Welcome, guys, to another episode on our floating point series. The goal is to be able to build a multiply and accumulate function, which we can use over and over to do other more complicated things, like machine learning. Um, and without further ado, I'd like to start off by pointing that in our previous episode, we talked about this basic notation of how the floating point numbers work. And when you express floating point numbers inside a machine, the number which mathematically look like this, where minus 1 to the power sign, 2 to the power exponent, and 1 dot f, it's actually written inside machine as just a sign bit, which is here. The exponent has a bias, so it's e plus 127. In 32-bit or single precision, the bias is 127. For double precision, it's different. Now, the final 1.f format of the remaining part of the number is just written down in the last 23 bits as f. So this gives us the 32-bit single precision number. Now, if you want to review this in more detail, just look at my previous episode, which is on floating point numbers. Today, we're going to cover how would you multiply two numbers. Multiplication is very useful operation if you're trying to implement neural nets. And so the way you would do this floating point multiplication is that, let's say we have two numbers and we have expressed them in the machine format. So the first one has the sign S1, which is a single bit, and then you have 8 bits of exponent E1 and then 23 bits of the remaining value F1. Um, and then you have another number S2, E2, and F2. Now, in mathematical notation, you can write this as minus 1 to the power s1, 1 dot f1, 2 to the power e minus 127. Remember that e1 has a bias of plus 127. So if you want to extract the original number, the exponent there would be whatever you read in the machine format minus 127. And the same thing for the second number. Now, when you try to multiply these two mathematically, you would get this minus 1 to the power s1 plus s2, 1 dot f1 times 1 dot f2, and then finally the exponent would become uh, E1 minus 127 plus E2 minus 127. And so what we can do then is that we have to convert this back to the original machine format, because that would be our final floating point value. So keep in mind that S1 plus S2, when you add this, is only one bit. The sign is only one bit. So you have to do modulo 2, right? When you do this S1 plus S2. If it becomes 2, then it becomes a 2 mod 2, which becomes a 0. Problem with 1.f1 and 1.f2 is that if it becomes larger than a format of 1.f1, if it becomes 2 or more, then you have to renormalize this part, right? And you have to renormalize this to a format of 1.f3, which is by dividing by 2, right? So you have to extract, divide by 2 and renormalize this multiplication part. So that's another step. The final step for getting the exponent is that if you have this, then the exponent that you write in the machine format is the actual mathematical exponent plus 127. So it'll become E1 minus 127, E2 minus 127 plus 127, right? And if you do the math here, that 127 that you do as a plus will cancel out one of these, as I show here. And what you would be left with is E1 plus E2 minus 127. And what is this? This is essentially the original machine format E1, machine format E2, and you just subtract the bias. Instead of adding the bias, you subtract the bias. So that's the final method. So now let's apply this to an example. Let's take 1.5. 1.5 can be written as, in a machine format, can be written as a floating point number, single precision, as 0, 127, and zero point 0.5. And it's 127 because exponent is really 0, and when you write the 0 as a bias format, it becomes 127. And the same thing here. Now, what you would do is sign is 0 plus 0 becomes 0. When you do the 1 dot 1.5 times 1 dot 1.5, it becomes 2.25. Now remember, this is not in 1 dot f3 format, right? 1 dot f format. So you have to divide by 2. So if you extract 2 from this, it becomes 2 times 1.125, right? And this is good because we can then take this 2 and put it in the exponent. Now the exponent here is 127 plus 127, and then our formula was add the exponents from the machine format and subtract 127. So 127 plus 127 minus 127 is still 127. Now remember that we have this 2 left over from our um, significant portion of the fraction. And so we bring this 2 here and it becomes plus 1 here because it's multiplied by 2. It adds 1 to the exponent. So it becomes 127 plus 1, which is 128. So I guess all this while you've not been able to see this lower half that I've been describing. But what I've been saying is that the net result is that at the end of it, you would get 0 for the sign, 128 for this exponent, and 0.125 for this significant portion. And there are websites available that'll convert any number, like if you say 2.125, they'll convert this. And you can see that this matches. This website reference is given up here. And I just try to convert 2.25 into floating point number from IEEE 754 notation. And you can see that this matches. This is 0, 128, and then 0.125 for this fraction. So that is essentially it for a floating point math. And you can see that it's pretty straightforward, except for a few quirky conventions like handling this bias, right? And also renormalizing once you multiplied these to the significant portion. Um, it has to be renormalized because it can become 2 or larger. And if it becomes 2 or larger, remember you have to come back into the 1.f format. So that's what we do here. So that's it for this episode, guys, and hopefully you liked it. If you did, do subscribe to my channel, and I'll bring you more videos in this series and continue all the way up to where we can probably demonstrate some machine learning capabilities using functions that we can control, especially multiplication operations, etc. Once we understand these, we can easily implement them in hardware and and hopefully uh, do some simple applications that can demonstrate the power of simple math that can be used to do fairly interesting stuff. So that's it for this episode. Thanks a lot, and I'll see you in another episode. Until then, take care and bye bye.